Hello, y'all. Welcome to lesson 82 of my DP chemistry curriculum. Today we're going over reactivity 2.2.4 and 5. So 2.2.4 is about activation energy. E sub A has a minimum energy that colliding particles need for a successful collision leading to a reaction. And from that, we'll be talking about Maxwell-Boltzmann energy distribution curves to explain the effect of temperature on the probability of successful collisions. Following that, we'll talk about reactivity 2.2.5, which is where catalysts increase the rate of reaction by providing an alternative reaction pathway with lower activation energy. You'll remember this is a phrase I said you must remember on our last video. From there, we'll be able to sketch and explain energy profiles with and without catalysts for endothermic and exothermic reactions. We'll construct Maxwell-Boltzmann energy distribution curves to explain the effect of different values for EA on the probability of successful collisions. So we're just going to go over a whole bunch of stuff that's all interconnected between 2.2.4 and 5. So starting with activation energy. So as we just said in that previous reading, activation energy, or E sub A, I use capital A. I think the DP uses lowercase a. It doesn't matter too much. Is specifically that like energy you need. It is the energy required required to break bonds in reactants. Because whenever we have a chemical reaction, we first have to break the reactants apart, and that's to achieve a transition state. So these transition states are a little weird. Um, we don't really have them in our chemical equations or chemical reactions that we write out, but this is specifically, it refers to species, or to species specifically in chemical reactions that exist between reactants and products. So it's kind of like this intermediary where bonds are broken, and new ones are formed. So it's kind of like this middle part. It's kind of like what's happening in the arrow when you do like A plus B reacts to form C plus D. This is kind of our transition state. It's that arrow. It's like what's kind of going on in between. So we have activation energy as the specific energy needed to achieve that. So we used to look at like energy profile diagrams. When we looked at the energy profile diagram for an endothermic or an exothermic diagram, we would look at this type of profile. So this would be endothermic, and this would be exothermic. And we would refer to the increase in delta H. So this would be a positive delta H. This would be a negative delta H. Oops. Trying to get rid of these dots right here. And this would be our energy profile diagram. We would know that our reactants and our products are reactants and our products, and that's all we would really have. But this isn't actually what an energy profile diagram looks like. So we're going to start looking at real actual energy profile diagrams. So I'll try and make these as clean as possible so that if you're copying them down, you can get a better version. So this is our potential energy or chemical potential energy. This is going to be our reaction coordinate. What I'll do is I'll copy this because we're going to do one for endothermic and one for exothermic. Oops. So here on one side, we'll do this is endothermic. And so in endothermic, we start at a lower energy and we achieve a higher energy. I'm gonna kind of give myself a little space here. So what actually happens? Well, we actually need to put in more energy than we usually expect. And that's to account for the activation energy. So our endothermic profile kind of looks like that. Got this little bump. And if we look at our exothermic, where we're releasing energy, once again, we still have to put some energy in, and we get a profile that looks a bit like that. So here's our reactants, here's our products, here's our reactants, here's our products. But the big difference in this curve is now we have this, this long bar right here that kind of refers to the top of the bump, to our energy. And we actually have 3 points of interest, the amount of energy in our reactants, the amount of energy in our products, and the top. And we have from our reactants to the top energy, this is our activation energy. This is the energy that we must put into our reactants to get the reaction started. Furthermore, we can list our transition state, which is up here at the top, transition state. And lastly, with this diagram, we can list the change in energy. So this gap is still going to be plus delta H, while this gap is still going to be minus delta H. So this is what our actual energy profile diagram looks like moving forward. We're always going to be accounting for the activation energy. Now, we learned about something that changes activation energy. We learned about catalysts. Catalysts lower activation energy. So what we're going to do is we're going to represent the catalyst with a dotted line. So when we have a catalyst, we get this lower activation energy. And this is why they speed up reactions. You get so much more from so much less energy input. So that catalyst is represented right here in this yellow line and that yellow line. So now we can see how catalysts start having an influence on chemical reactions, not by adding energy or pulling energy away or speeding up the particles. They just decrease that barrier to entry. So that is our energy profile diagram, including activation energy. So how do we actually utilize this stuff? Well, here comes what we call the Maxwell-Boltzmann Boltzmann distribution. So this allows us to actually start looking at almost individual particles in a reaction. So what a Maxwell-Boltzmann distribution does is it's based on temperature. And because temperature, temperature is a measure of average, and the key word here is average kinetic energy, then some particles have high energy and some have low energy, but most have a middle amount of energy. But this curve shows these particles and it represents energy of particles against the number of those particles, which sounds confusing, but once we look at a Maxwell-Boltzmann distribution, we will be able to understand what we mean. So a Maxwell-Boltzmann distribution is yet another graph that you're going to have to know how to draw and know how to read. And it has the two axes. The two axes are simply energy and number of particles. And a Maxwell-Boltzmann distribution looks like this. All right, there are some super key aspects about this. What you'll notice right off the bat is that most particles reside here. So the area under the curve represents where most particles are. So most particles have mid energy, like a middle amount. We'll just say average amount of energy. Some particles, on the other hand, but much fewer, have very little energy. Few particles with little energy. And then we also have some on this side that have high energy. Some particles with high energy. So the curve itself just kind of shows you where particles exist, what region. And usually you have few particles with high energy, few particles with low energy, with the majority of particles being right here in the middle energy. And this is kind of just describing an average. If you arrange children in a classroom by height, you'll get a curve. The couple distinctive features of a Maxwell-Boltzmann curve is they always start at the origin. So a big note here is that we start at the origin, always. Start at origin. That's because particles aren't going to have necessarily like zero energy overall. Your particles probably have more than zero energy. No energy is temperature equals zero, essentially. Um, the other key aspect here is that this end is kind of like an asymptote because there could theoretically be one particle that just gets shot out and has crazy amounts of energy when all the other particles are putting it together. So those are two key features. The last key feature of Maxwell-Boltzmann curve is that you always add activation energy. This is the energy by which a particle will react. And the beautiful thing of a Maxwell-Boltzmann curve is that we can see our high energy particles are generally what we consider to be past our activation energy, meaning that this fraction of particles all have enough energy to react, which means that some of them will likely react, while these particles do not. So that's our Maxwell-Boltzmann distribution. The thing about it is we can now make some adjustments. This curve makes quite a few adjustments when we change one of two things, temperature or catalyst. So let's look at the effect of temperature. So if we create our Maxwell-Boltzmann distribution, and this time I'm going to be kind of lazy with it, and just our base curve looks like this. So this is just T initial. Now, if we heat it up, if we heat all these particles up, right now our energy for T initial, our average energy is kind of right down the middle. That's T average. If we heat up our curve, our average is going to shift to the right. So this might be our average for T average hot. The question is, what happens to the curve? As we pull it to the right, as we pull that to the right, it's kind of going to shift and flatten down. It's kind of like if you have like a mound, as you move that to the right, it's kind of going to wave over and move with it. But instead of the whole thing shifting, it kind of flattens out a little. So we get a curve that looks like this. Now, if we superimpose our activation energy, oops, EA, you'll notice that as we increase the temperature, we have a lot more particles that have an activation energy greater than in our original trial. So you can see how increasing the temperature increases the rate of reaction because you have now more particles that have energy that can react, and the Maxwell-Boltzmann distribution helps show this. The overall area under the curve is still the same, but pretty much we added all this by removing it from here and kind of shifting it over. Now, what happens if we freeze it? Well, our T average is going to decrease. T average holds. And almost inverse to that, we now have a curve that looks like this. And so you'll notice this curve has less particles. And you can't even see the blue highlighter, less particles that can react because our curve shifted the other way. So temperature has a great effect on our Maxwell-Boltzmann distribution. You'll notice the peaks change height. Oh, I want to do that in a different color. You'll notice the peaks change height and the fraction of particles all change. So the other thing that affects our Maxwell-Boltzmann is the effect of a catalyst. And we know that catalysts, their main job is to lower EA. So if we throw a catalyst in this mix, we can put it right here with a catalyst. And now you have all these particles that have enough energy. So catalysts are really shown on a Maxwell-Boltzmann distribution curve to show their effect because they're by decreasing the activation energy, there are a lot more particles that now have enough energy to react. So hopefully this helps you understand a little bit about Maxwell-Boltzmann distribution curves, activation energy, and the effect of catalysts and temperature. Have a great night.